We have talked about constant air volume systems. They are not as common as they once were, but still exist in many different applications across our bases. Hopefully now you feel comfortable with how the various configurations of CAV systems are controlled. Today we're going to examine VAV systems, or variable air volume systems. VAV systems are ones that have the capability to modulate total airflow in the system. Such systems are becoming the norm, especially in commercial buildings. The primary reason for this is the fact that they are far less energy intensive. We will talk about why this is in this lesson by examining the fan affinity laws, which are quite similar to the pump affinity laws we talked about a few lessons back. We will look at the two most common configurations of VAV systems and how such systems are controlled. We will look at pressure independent versus pressure dependent VAV boxes, as well as discuss reset schedules for both the supply air temperature as well as the static pressure set points. The objective for this lesson will be for students to comprehend typical configurations of variable air volume systems, the potential such systems have to save on energy, and how such systems are typically controlled. The corresponding samples of behavior will be: identify the two variables, which could be manipulated to adjust the thermal load provided to the space by an air system. Explain how variable air volume systems can save on energy when compared to constant air volume systems. List the three options discussed in this lesson to control for the flow rate of air in the order of their ability to save on energy. Explain why outlet dampers are not advised for modulating the volumetric flow rate of air. Identify the components of the control loop, which incorporates variable inlet vanes. Discuss the interaction between VAV box damper positions, static pressure in the air system, and fan speed in terms of fan and system curves in a system which utilizes a VFD. Identify why we apply minimum frequency settings for our VFDs. Describe the operation of a VAV box, which includes a reheat coil, when the system is in cooling mode, when it is in heating mode, and how the VAV box operation transitions between the two modes. List ways in which we can reduce energy waste that can occur in a VAV with reheat configuration if we are both cooling down and heating up the same airstream. State reasons why we should not get too aggressive with our supply air temperature reset schedule. List the two common indicator variables, which are used to reset the supply air temperature set point. Identify the system disturbance, which pressure-independent VAV boxes work to mitigate. Identify the components of the cascade control logic, which can be utilized in pressure-independent VAV boxes. And identify potential limitations that present themselves when implementing a static pressure reset schedule. Let's review how we bring heat to and from an occupied space. The amount of sensible heat being brought into or out of a space follows this simple equation. As we have talked about before, the room air temperature is typically the control variable. That means that is the variable we want to keep at a certain set point. As the heating and cooling requirements of the space, represented by Q sensible on the left side of the equation here, change throughout the day and year, we need to have an air system capable of modulating to meet those ever-changing requirements. We can do that by keeping the volumetric flow rate, or CFM, being cycled through a space constant while modulating the supply air temperature. Or we can adjust that volumetric flow rate and keep the supply air temperature constant. This second approach is predominantly what is used when we are trying to control room temperature with a VAV system. However, when we talk about VAV systems with reheat capability, the first approach of keeping the CFM constant while varying the supply air temperature will be used when the system is in a heating application. Kind of confusing, I know, but we will walk through the various system configurations and discuss how they are controlled across a variety of scenarios. For now, just know that to properly control the system to maintain a room air temperature at set point, it is best to maintain one of these two variables constant while adjusting the other. So, we have already stated many times that the VAV systems are less energy intensive than the CAV systems. By that we mean VAV systems consume less energy to operate, because they can slow down the fan speed, thus save on energy the fan consumes. So how much energy savings really comes from slowing down the fan? Well, we have to turn to a set of equations known as the fan affinity laws. And that will be our first topic of discussion today. The first equation in the fan affinity laws states that the speed of the shaft is proportional to the flow rate of air the fan is putting out. So what is the significance here? Basically, if the fan is operating at state 1 with a flow rate of 10,000 CFM and a speed of 1750 RPM, and we know we want to cut the flow rate in half, we can determine the required speed of the shaft that will give us that outputted CFM. In this case, it would be 875 RPM. Now, if we know how much to slow down the shaft, we can turn to another fan affinity law to determine how much energy that is really going to save us. This next law shows the relationship between power consumed by the fan and the speed of the fan. It is actually a cubic relationship. So say the fan was pulling 10 horsepower when it was running at 1750 RPM. We want to cut the flow rate in half, so we subsequently run the fan at 875 RPM. The resultant power being consumed would then be 1.25 horsepower. That is an 87.5% reduction in power being consumed. That is the reason why variable air volume systems have become the norm, because of the incredible potential to save energy at part load conditions. Now, just like with the pump affinity laws, the fan affinity laws don't tell the whole story. That stated 87.5% reduction in fan power consumption would be for an ideal situation. That ideal situation would include a situation where the fan efficiency, the efficiency of the motor driving the fan, and the efficiency of the VFD controlling the fan motor all stay constant. That is never really the case. When we use a VFD to slow down the fan, these three efficiencies often decrease a bit. The efficiency of the fan, that is, its ability to convert the power of the rotating shaft into increasing the pressure of the air and subsequently driving flow, does not change drastically at low loads. However, the efficiency of the motor, that is, the ability to convert electrical power into rotating a shaft, does drop off at low loads. Look at how motor efficiency typically degrades with decreased load. Similarly, the efficiency of the VFD decreases at part load as well. The VFD has some fancy solid-state electronics in it that vary the frequency of the power. Thus, it uses up some energy itself. Therefore, the efficiency of the VFD is just the ratio of how much power it sends to the motor divided by how much is fed into the VFD. We could walk through an example of just how much energy consumption is reduced at part load, and compare it to the idealized energy reductions the fan affinity laws would predict. Such an example would closely mirror what we did in the variable flow hydronic system lesson. But to save you the pain, and for the fact that we have a lot to cover in this lesson, we will instead just show you this table. This table shows the actual power consumption you would typically see when reducing the flow rate from its maximum speed. Notice the bottom row of this table provides you the theoretical energy consumption that would be calculated from the fan affinity laws. It also contains values for 3 different ways we can use to control the volumetric flow rate of air: outlet dampers, variable inlet vanes, and variable frequency drives. Up until this point, we have only discussed the use of the VFD. There are 2 other common ways of reducing the airflow rate of the fan: outlet dampers and variable inlet vanes. We will provide a brief discussion in the minutes ahead of how these types of systems work, but with a decrease in cost and increase in performance of VFDs in recent years, the VFD option is predominantly the mechanism you will see in the buildings you work on. Alright, so let's go to the first of the 2 system configurations we are going to talk about today. This is a cooling-only VAV system. The general layout of this system should look familiar. However, we remove the boiler and the associated piping and heating coils. This system serves 3 different zones, but real-world systems can serve many, many more. Here's how the system works. First off, back at the air handling unit, we have the chilled water control valve modulate to maintain a constant discharge air temperature coming out of the air handling unit. So that is a closed control loop. The set point for that discharge air temperature should be around 55 degrees Fahrenheit. This temperature will ensure that some dehumidification takes place back at the cooling coil. We're not typically going to directly control for humidity. That is, we are not measuring the humidity in the space and controlling the system accordingly, but maintaining a supply air temperature of 55 degrees Fahrenheit will allow us to indirectly control for it. We did discuss the idea of indirect humidity control towards the end of last lesson, so go review it if need be. So now we have that temperature in the supply air duct at around 55 degrees Fahrenheit, and we are capable of providing cooling to the various zones. The cooling requirements of each zone are going to vary throughout the day and year. So going back to that same equation we have been looking at, the only way to maintain the room air temperature set point is to modulate the amount of 55-degree air that gets sent into the space. We do this by use of a VAV box. This box has a damper located inside of it that can be modulated. The temperature sensor in the space will measure the temperature and send that information to the controller located in the VAV box. If the room temperature starts to drop below set point, the controller will tell the damper to modulate towards closed, as too much cooling is being provided. If the temperature in the room starts to rise above set point, the damper is commanded to modulate open, because more cooling is now being needed. So at each zone, there's another independent closed control loop. The room air temperature is the control variable, and the VAV box is the controlled device. Now, as we alluded to before, there are three ways we typically control the volumetric flow rate of air. The first is called outlet dampers. The system configuration we just walked through has outlet dampers, as those dampers in the VAV box are on the outlet or discharge side of the fan. As those dampers close, we can reduce the volumetric flow rate of the air going into each space. However, the static pressure in the supply duct will increase, just like we saw in the hydronic systems when the valves closed. If we don't install some device to change the speed of the fan when the static pressure increases, the operating point of the system will just ride the fan curve. Let's illustrate this. Say we have a system with all the VAV box dampers wide open. Here's the system curve they are operating on. Then the cooling load in some of the zones starts to decrease, and some of those dampers start modulating towards a closed position. This will effectively change the system curve. If the fan doesn't have the capability to slow down its speed, the operating point will just ride the fan curve. So this is one way to utilize variable air volume systems. However, it is not advised. For one, it has the potential to damage the fan. See that do not select to the left of this system curve line on the fan performance data here? That region to the left of the line is called the surge region, where slight adjustments in the static pressure seen by the fan drastically change the volumetric flow rate the fan pushes out. The fan will surge back and forth, and this can be quite damaging to it. The second reason this is a less than optimal way to vary the volumetric flow rate of the system is that it is not very energy efficient. Depending where you start and where you stop when you're riding the fan curve back to the left, the power consumption of the fan will usually decrease, but there is a potential it could increase. Again, just look at the chart depicting the fan power consumption at reduced flow. The outlet dampers control approach doesn't fare nearly as well as the variable inlet vanes or the variable speed drive options. Now if the fan can't slow down, and the VAV dampers located just above the space that they're serving start to close, it's going to get loud for the occupants. So oftentimes these systems have another damper located just downstream of the fan, back in the mechanical room. If the VAV dampers start to close, this will drive up the pressure in the supply ductwork. We can place a differential pressure sensor in that supply ductwork. Now, this is often referred to as the static pressure sensor, but what it is really doing is sensing the difference in static pressure between the inside of the duct and the outside of the duct, which would be representative of the internal pressure of the building. So again, if the VAV damper closes and the static pressure in the supply duct increases, we could have that additional damper on the discharge side of the fan start to close in order to maintain a static pressure set point. This type of configuration still just changes the system curve, and we ride the fan curve back a bit. But now a good part of the pressure being dissipated will occur at the discharge air damper just downstream of the fan, out of earshot of any space occupants. So the second approach to control the flow through the air system is that of variable inlet vanes, also called inlet guide vanes. We would control the system the same as before. When each zone requires less cooling, its VAV box damper would modulate back towards a closed position accordingly. This will drive up the static pressure in the supply ductwork. We will again place a differential pressure sensor in that supply ductwork. The location of such a sensor is usually determined by the TAB, or Testing, Adjusting, and Balancing subcontractor during the balancing process, and it is typically 2/3 to 3/4 of the way down the supply duct run. We will impose a pressure set point we want the system to maintain. So, if the VAV dampers close a bit and the pressure rises above that set point, we will have a controller send a signal to some mechanism that will now change the fan operation to bring the pressure down a bit. During the hydronic lessons, we only discuss the use of the VFD to perform this function. And we will talk about the use of VFDs in air systems here in a second. But first, let's talk about an older technology that is at times still used to change the fan curve. We install these variable inlet vanes or inlet guide vanes on the suction side of the fan. These are basically dampers, as you can see here. They can be mounted in the ductwork just prior to the fan or internal to the fan itself, but they are always on the suction side of the fan. Here is how they work. If VAV boxes further down the duct path are closing, the rise in pressure in the supply ductwork will result in the controller telling these inlet guide vanes to close a bit. When they close, they do two things. First off, they are further restricting the flow of air. Thus, the system curve becomes a bit more restrictive. However, they pre-rotate the air prior to it entering the fan. This reduces the pressure increase across the fan, thus actually changes the fan curve. So, inlet guide vanes modulate to maintain the static pressure set point in the supply ductwork, and they do so by changing the fan curve. The speed of the fan actually doesn't change, as we will see happen with the VFD. The fan curve changes due to the induced rotation of the airstream as it enters the fan. After the vanes adjust, the new operating point of the fan will be the intersection of the new system curve and the new fan curve. Resultant fan curves as the guide vanes close more and more can be seen in this plot. Compare this to the different fan curves that result from a VFD actually slowing down the speed of the fan. The big takeaway here is that since we are changing the fan curve when the pressure in the supply duct rises, we are essentially going to achieve the reduction in the amount of energy it takes to push the air. In the case of outlet dampers, we actually saw an increase in pressure across the fan. If we can reduce the pressure produced across the fan when the reduction in flow is desired, as we are essentially doing with inlet guide vanes, we see greater energy savings. This can be seen back at the table we've been showing throughout the presentation. But looking at this table, though use of inlet guide vanes is more energy efficient than outlet dampers, they're still not as good as using VFDs. So let's further our discussion on VFDs, as they have become the norm for controlling flow in variable air volume systems. Control of a system with a VFD is very similar to how we controlled the system with inlet guide vanes. As the cooling load in each respective zone is reduced, the VAV dampers will close. This will drive up the static pressure in the supply ductwork. The rise in pressure will indicate to the VFD that less flow is needed. Thus, the VFD will reduce the speed of the fan at which the fan operates. This will change the fan curve. Again, it is the intersection of the system curve and the fan curve where the system will truly operate at. Since there's a lot happening here, it's probably best to walk through an illustration as to what exactly is happening. Imagine the VAV dampers for the three zones are partially open. Then the load at zone 2 starts to decrease. Thus the VAV damper starts to close. The closing of that damper is going to raise the static pressure that is being sensed in the supply ductwork. Basically, the closing of the damper makes the system more restrictive. Thus the system curve is changing. Initially, the operating point will just ride the fan curve back. And you can see here that, in fact, the pressure in the system is increasing. This will be realized by an increase in differential static pressure in the duct. which in turn will tell the VFD to slow down the fan. When the fan slows down, essentially the fan curve is now changing. As you can see, though each zone has its own individual control loop with a temperature sensor, controller, and VAV damper, and the fan has its own individual control loop, they all affect each other. Changing in a VAV damper's position changes the system curve, which will subsequently change the pressure in the system. A change in system pressure will result in the VFD speeding up or slowing down the fan, which effectively changes the fan curve. Just like with variable flow hydronic systems, these VAV systems are very dynamic, and changes in fan speed and VAV damper positions are constantly occurring, many times simultaneously. The previous illustration just showed what is happening in discrete steps for you to wrap your head around this very dynamic system. So that is how a VAV system which incorporates a VFD works. Now, there are some limitations as to how much we can slow down the fan, just like we saw with hydronic systems. We typically don't allow VFDs to control fans to operate at much less than 10 Hz, that is 1/6 the max operating speed of 60 Hz. The reason we do this is that at such low loads, the motor efficiency and VFD efficiency drop off drastically. Thus, operating in such ranges can actually drive up the amount of energy being consumed. Sometimes it is deemed acceptable to take that energy penalty by reducing the speed below this point of diminishing returns, but we can save discussion for when such instances may occur for the LMS. So we have to have some mechanism in our system to ensure we allow for minimum flow to occur. In the hydronic system configurations, we either used a single three-way valve, which ensured flow would always occur in the system, or we incorporated a bypass loop. In a variable air volume system, we don't need either of those. We just set a minimum position the VAV box is allowed to close to.